All right, so what we're looking at here is what we call the conjugate root theorem, which is a really nice fact or property of complex numbers, and we solve complex numbers. What the conjugate root theorem tells us is if the polynomial has real coefficients, so it's really important, it has to have real coefficients, then if a plus bi is a solution, a minus bi is also a solution. So if you think back to the questions that we just solved in the last exercise, our solutions often turn out to be something like 2 plus or minus 3i, 1 plus or minus root 7i on 2, or whatever it was. So it's 1 plus complex, 1 minus complex. So it's the conjugate of it. And that's true for any polynomial equation that has real coefficients. So we can make use of that fact at different times to help solve our complex equations. Let's go back a little bit. Obviously, factorising a cubic. Now, think about our factorising cubics, we certainly use division. All right. Now, there is a nice method that I'll get you to look up. What is it called? It's called synthetic division. All right. And so, what synthetic division is, if we find our value that makes p of z equal to 0, so find our first root. 1's not going to work, so I'll try 2. P of 2 is equal to 8 minus 4 minus 2 plus 10. So if I make it a negative, I reckon a negative will get close. P of negative 2 is minus 8 minus 4 plus 2 equal to 0. So P of minus 2 works, so Z plus 2 is a factor. So we might do our normal division, and we'll look at that in a minute. What we can do for our what we call synthetic division, negative 2 is our solution. Put it out the front and put the coefficients of Z up. 1, negative 1. In fact, I'll put them up here. 1, negative 1, negative 1, and 10. All you do is bring the first term down. Let's use the right pen. Bring the first term down, which is 1. 2 times 1 is 2. Oh, sorry. Negative 2 times 1 is negative 2. Add them together. Negative 1 plus negative 2 is negative 3. Negative 2 times negative 3 is 6. Add them together is 5. Negative 2 times 5 is negative 10. Add them together is 0. So in this, that last term there is your remainder. And these are the leading coefficients of x squared, x, and constant. So what we're saying then is that this factorises to, I've got 1z squared minus 3z plus 5. Negative 2 was the other solution, so that gives me z plus 2 as my other factor. Okay? So that's what the division is. I'll go over here and do our division as we learned it primarily last year. Z plus 2 is a factor. Obviously, you can use your repeated factor method as well. Z cubed minus z squared minus z plus 10. Let's get a z squared up there. Z squared times z cubed plus 2z squared. Subtract them. So we get minus 3z squared minus z minus 3z. Subtract them. And we get our minus 2 again, yeah? 5. Plus 5. 5z plus 10, we get 0. So if you have a look as you go through, the key numbers are all the same, aren't they? So it's just another way of really coming up with those remainder terms. But anyway, once we've got our two factors, let's go back into the question. So I'll write it in red. So that's what it factors to. I want to solve it equal to 0, so that one's okay. I've got to factorise the other one. So we know that z plus 2 is equal to 0, or z squared minus 3z plus 5 is equal to 0. So z equals negative 2 is one solution. I'm going to complete the square. Z minus a half the middle term is 3 on 2. Square that is 9 on 4. So I plus 9 on 4 minus 9 on 4. And 5 is the same as 20 on 4. So that gives me, squared. Z minus 3 on 2 all squared equal to 11 on 4, take it across. Negative 11 on 4. So I'm just going to go with z is equal to 3 on 2 plus or minus, introduce an I squared. So I'm going to have root 11i on the square root of 4, which is 2. All right, so there's my highlight. There's my solutions. All right, so the cubic division is sort of your call, how you would like to approach it. Now, I guess, look at something like z to the 4 minus 81 is equal to 0. Immediate inclination would be, okay, well, z to the 4 is equal to 81. Take the fourth root. So 81 is the same as 3 to the power of 4. Fourth root of that, and we get z equal to 3. Oh, well, plus or minus 3, in fact, because it's an even power. But with z to the 4, we're expecting possibility of 4 solutions, not all distinct, but 4 solutions. So we can't necessarily just do that. All right, we've got to factorise it through first, at least until we get to the, well, not even at a squared point. Because if we make use of the fact z to the 4 minus 3 to the 4, that's the same as z squared minus 3 squared squared, and that's a difference of squares, isn't it? So that's a squared minus b squared, so that means I can write it as z squared minus 3 squared, z squared plus 3 squared equal to 0. So now hopefully we can see in here z minus 3, z plus 3, and that's going to give me a z, well, if I come over here first, z squared minus 3i squared to make it a difference. So then I can make it as minus 3i z plus 3i. So now we can see that z is actually equal to plus or minus 3 plus or minus 3i. So you've just got to be a little bit careful to factorise it out fully. All right. So these ones are just a little bit more challenging because we don't do a lot of factorising, or we haven't in methods in particular. What are we doing in enhanced? We've done a little bit of polynomial extra stuff by now. But we'll just take it a step at a time. So z to the 4 minus z squared plus 5. We can see that it's basically a polynomial, a quadratic. So to make it look more like a quadratic, if we just let u equal to z squared, that means u squared is z to the 4. So if I do that substitution, that gives me u squared minus u plus 5 equal to 0. And now I can clearly see that it is a quadratic. How does that factorise? Doesn't really. So we can just complete the square, I guess. What if we just complete the square? So we're just going to write that as u minus a half all squared So that's plus a half squared minus a half squared, which is minus a quarter, plus 20 on 4. So I get u minus a half all squared. What's that? Plus 19 on 4 equal to 0. U, hopefully we get into the habit now, it's going to be a half plus or minus the square root of 19i on 2. But u is not what we started with. We started with z, and u is equal to z squared. Therefore, z squared is equal to 1/2 plus or minus the square root of 19 on 2i. So we can in fact just write it as plus or minus the square root of. As ugly as it looks, at this point in time, that's a really acceptable answer. Okay, so this last one here, believe it or not, it is one of those ones that we can factorise by inspection. If I look at the coefficients of all of the terms, I've got 1 by I by 4 and 4i. If I multiply the coefficients of those first ones together, I end up with the last term, which suggests that I can factorise by grouping. So if I take a z squared out the front of the first term, that leaves me with a z minus I. And then if I take a negative 4 out the front of the second term, that also leaves me with a z minus I. And now I get z minus I, z squared minus 4 is equal to 0. So I get z is equal to I, z is equal to plus or minus 2. You notice this is the first one that hasn't had a conjugate pair as a solution. And that's because our coefficients are not all real coefficients. Okay, so we could do a long division and whatnot at that point in time, but really this year it's not going to be a part of our complex course because it's messy and it's not really practical, but certainly factorising by inspection is practical and something that you could expect to do. All right, so this was all leading us to what we call the fundamental theorem of algebra. And all that really tells us is that for the polynomial p of z, if it has a degree of n, it has n roots or n solutions. Now, the thing to be aware of, they may not be distinct. So if you think of even just the polynomial x squared minus 2x plus 1, x squared suggests it should have two solutions, x minus 1 all squared. So 1 is my solution, but there's only one solution, one distinct solution. But clearly, x minus 1 gives me two solutions, two factors. So you may not get distinct solutions, but that's how many solutions you can expect. So every polynomial of degree n can be factorised into n linear factors, all right, but they're not necessarily non-repeated. Okay, so this is where we make use of our conjugate root theorem. We're told that if z is equal to 1 plus 2i is a solution, find the other solutions to that equation. So the first thing we notice is that this equation has all real coefficients. So if 1 plus 2i is a solution, 1 minus 2i is also a solution. Okay, so what does that mean? If 1 plus 2i is a solution, z is equal to 1 plus 2i, it means that z minus 1 plus 2i is a factor. And if 1 plus 2i is a solution, 1 minus 2i is also a solution. So z minus 1 minus 2i is a factor. The reason I want to do this is because then I'll expand that. Minus 1 minus 2i. Z minus 1 plus 2i. There's two factors. So if I expand and multiply these together, so each term, so I'll just z to that, z to that, yeah? So I'm just going to write z squared minus z plus 2iz minus 1 into everything, minus z plus 1 minus 2i, and now negative 2i. 2iz, can I squeeze down underneath? Plus 2i minus 4i squared. If we've done it right, all the I terms will cancel. So positive 2iz minus 2iz minus 2i plus 2i. 4i squared is negative 1 for I squared plus 4. Group all our terms together, and I might come over here now. I get z squared minus z minus 2z plus 1 minus 4i squared is going to be plus 4 plus 5. So there's a quadratic factor of that expression. Okay, so now I can approach it two ways. The way in which I want you to consider it is, I know that z squared minus 2z plus 5. I could do a division. I could divide z squared plus minus 2z plus 5 into that cubic. The way in which I like to do is, that's one factor, which means I have one linear factor left, and it could be of the form az plus b. If I expand this, but I don't have to expand the whole thing. If I expand this, the first term I would get would be az cubed. And that's going to be the only cubed expression I end up with. And that az cubed has to be the same as z cubed. So it has to equal z cubed. Therefore, a must be 1. If I do the same thing, my very last term, I could go through the whole expansion. The very last term I get, I'm going to get b times 5, which is 5b. That's the only constant expression. And 5b has to equal 5. Therefore, b is equal to 1. So my last term, the az plus b factor, is z plus 1. And so that's my factored solution. All right. So my other solutions are, well, 1 plus 2i. That's one solution. 1 minus 2i is a solution. And z plus 1 gives me the other solution. Like that. So therefore, my solutions are, what I say, 1 plus 2i from the question, 1 minus 2i from the conjugate of that, and what did we say, negative 1. Are the three solutions. All right. Now, this is more genuine, I guess, year 12 work, which means instead of sending you to the year 12 textbook, I'm going to get you to do these questions in here on the sheet. There's some cubic ones, so you might do a division. You'll have to do a synthetic division or a polynomial division. Synthetic's a bit different with the coefficient of 3 out the front, but we can still do it. Z to the 4, similar to the example previously, so a little u equal to z squared, but that looks like it'll factorise a bit nicely, z plus 2 plus 1. And here, if we put u equal to z cubed, yeah, then we'll end up with a u squared minus 16u plus 16, and again, that looks a little bit